So a few people are on planes. Okay, I think I'm recording now. Okay, so yeah, so we're, so when I multiply by 4, and because I just made this up, this may not be very pretty. So when I multiply both sides by 4, what do I get for the first term?
6.
Yeah, I
X
get
squared.
6x squared. Perfect. Yeah, minus 8x plus 1 equals 0. Quick eyeballing of that makes me realize it doesn't look factorable. So then what do you guys prefer to do if you can't factor something to solve?
Quadratic formula.
Yeah, that's exactly what I would do. Quadratic formula. So quadratic formula, remember, is negative b plus or minus the square root of b squared minus 4ac over 2a. So doing that, I get 8 plus or minus 64 minus 4 times 6 times 1 over 2 times 6. So the thing that people often mess up, that will kind of make sure we don't mess up when we do this, is when the simplifying process and making sure we don't incorrectly cancel things out. What do we get inside the square root here? What's 64 minus 24?
40.
40, all right, yeah, anyone can say that, yep, over 12. So this square root simplifies. What can come out of the square root of 40? Oops. What's the perfect square in there?
10. I mean, sorry, not 10. 4 times
Yeah,
10.
10's left inside, right? 4 comes out as 2, and I agree, there's a 10 left inside. And now just be careful about how you simplify this. So if you're going to be able to simplify it, you have to be able to take something out of every term. And by that, I mean, do all 3 of these have something in common that I can reduce it by? What goes into all 3 of those numbers?
2.
2, yeah. So if I divide each of those numbers by 2, I get 4 plus or minus root 10 over 6. So those would be your 2 zeros, and there's nothing more you can do. So it has, again, if you simplify, it has to come out of each term. Okay, so not horrible, not beautiful though. But yeah, the key to that, similar to 7a, although 7a had a variable in the denominator, is just making sure you don't want to factor or use the quadratic formula when you have anything in a denominator. So multiply both sides to get rid of that. All right, in 2, I mean, initially looking at this problem, what are you thinking is the best way to approach it?
Like squaring the whole thing.
So yeah, so seeing a square root, it may be tempting to think of squaring everything. The problem is, remember what squaring everything means. It would mean on the left side, I multiply the entire side by itself, which looks like I get more of a headache than actually making things easier, right? If it was all multiplication, then absolutely squaring to get rid of that square root. But in this case, just squaring things is just going to make it more complicated. The nice thing is, though, what is only in a square root here? We'd be in trouble if there was a variable under the square root. Then we would do, and maybe that was what you were thinking, maybe then the only strategy is to isolate that variable under the square root and square both sides, which we haven't done in this class yet. Instead, though, because there's only a number under the square root, we can just use the quadratic formula. So if we use the quadratic formula, so we've got, let's just bring everything to one side, because again, only that number root 3 is under a square root. So in the quadratic formula, you just have a be 1, b be root 3, and c be 2. So it actually isn't that bad. It looks terrible with the root, but luckily it's only a number under a root. So you can use the quadratic formula like you normally would. So let's see how we did here. So if I do negative b, then I'll do plus or minus b squared, which would be 3 minus 4 times 1 times 2. Okay, so I purposely did this. So tell me what will happen under the square root.
There will be a negative number, so you need to use I.
Yes, exactly. So you have negative root 3 plus or minus. So 3 minus, oh, that's not 12 times 4, it's 2 times 4. So 3 minus 8, so it would be negative 5 over 2. And the only thing you have to know is what does a negative under a square root come out as? Whenever you see a negative under a square root, it should come out as what? So the 5 is going to stay inside, but a negative under a square root, or in other words, what is the square root of -1 equal to?
I.
I, right. So whenever you see a negative under a square root, it just comes out as I. So there'd be no real roots there, but that would be that would be the solution to that quadratic. So a negative under a square root would just come out as I. Yeah, so don't worry about, we're not going to do for this test the strategy where you have a variable under a square root and have to square both sides. No, you would just use the quadratic formula. So good question. So was that helpful, Erica?
Yeah, thanks.
What else? How do people feel about the difference quotient? Good. Or finding I'm trying to think of different things. Like, so if you remember what we covered in Thursday's class, we talked about domain and range, and we talked about finding zeros, factoring. We talked about finding intersections, simplifying using exponents, simplifying using the laws of exponents, then difference quotient, some of the application problems, which are doing the interest problems or the revenue and cost problems, which I think the revenues and cost problems end up being decently basic. Yeah, so all those. Any particular question or anything you want me to give an example of, or?
Can you go over 4B on the review sheet?
Sure.
It's like the double fraction problem, I think.
Yeah, let me find it. I've got it in front of me. Let me see, 4B, and then I'll open it up here. Oh yeah, okay, yeah, this is a good one, Eloise, to go over. All right, so let me go back in my iPad here. Hold on. It's gonna go, whoops. Okay, so number 4. Yeah, so this is, so that's the other thing that we put on the board on Thursday. Yeah, being able to do compositions is important. So if we look at 4B, so this is saying in the f function, I'm putting the g function, which is 2 over x plus 1. So this means for every x in that f function, instead of putting x, I'm putting 2 over x plus 1. So that means in the numerator, I'm going to have 2 over x plus 1. And in the denominator, where there's an x, I'm putting 2 over x plus 1, and then minus 1. And yeah, that is the composition, but you can't leave it like that. We can't leave it as a complex fraction. So the best way to deal with a complex fraction like this, especially because I don't just, if I had just one number in the denominator, say it was something like this, and I think this happens in part A, where you just have a single fraction in the numerator and a single fraction, say it was like this, in the denominator, then you can just solve by the division problem by multiplying by the reciprocal. Like I would just do this and then multiply across, but it's not so easy here, again, because I don't just have a single fraction in the denominator. I have both 2 over x plus 1 and the minus 1. So the best way to deal with that is to recognize that, okay, I just have one denominator out there, thank goodness, and it's x plus 1. So I'm going to multiply the entire numerator by x plus 1 and the entire denominator by x plus 1, which is totally valid because you're just multiplying by 1. So this means I'm going to distribute to the numerator x plus 1, and then I'm going to distribute to the denominator x plus 1. So when I do that to the numerator, I just get the x plus 1s are going to cancel. So I'm just left with 2. And when I distribute in the denominator, when it is multiplied by 2 over x plus 1, that x plus 1 will go away because it will cancel with the x plus 1 that is being multiplied by. But do not forget that you also are multiplying the x plus 1 times this minus 1. So that's what sometimes people forget. And this just is 2 over 2 minus x minus 1, or 2 over 1 minus x. So that would be the composition in simplest form without it being in terms of a complex fraction. Yeah, let's just, for this, since we're here, let's do part A, which is instead of a composition, we're just going to divide the two, but it's going to result in us needing to do a little simplifying. So f of x, which is x over x minus 1, divided by 2 over x plus 1. So notice how this simplifying is different. It's different because I just have a single fraction in the numerator and a single fraction in the denominator. So because of that, it's just easy to multiply, change the division to multiplication by multiplying by the reciprocal of the denominator. And then we can just multiply across. So it's x squared plus x over 2x minus 2. It's just harder when there's not just a single fraction in the numerator and denominator. Does that answer your question, Eloise?
Yeah, thank you.
Welcome. What if I asked, so let's go back to B. What if I asked you what the domain of that composition was? So think about if I had asked what the domain of f of g of x is. Think about what you would tell me. So with compositions, what matters? There are two things that matter when you think about the domain of a composition. What are those two things? Of course, it matters. The one people usually don't forget is it has to, if I look at the end result, it has to, meet that domain. So if I look at this end result here, what could an x be? Just looking at this, looking at 2 over 1 minus x. What's a no-no for x? I'll jump at once. What can x be in 2 over 1 minus x?
It can't be 1.
Right. It can't be where the denominator is 0. It can't be 1. Right. But with compositions, not only does the end result matter, but what also matters in terms of the domain is, remember, it has to pass through that inner function first. So that's why I write the composition this first, because at this stage, I always tell myself if there's a domain restriction, I make a little note of it because it has to pass through that function first. So looking at 2 over x plus 1, what else can x not be?
-1.
Right, it can't be -1, right? Because in 2 over x plus 1, if I were to put -1 in, I'd have 2 over 0. So realizing it can't be -1 and it can't be 1, just putting that together, I would say negative infinity to -1. I'm good till there. Then it picks up right after -1 and goes all the way to 1, and then picks up from 1 to infinity.
How come it can't be -1 again?
It can't be, oh, sorry, something's opening on my computer here. It can't be -1 because think about, here's a good example. Think about with a composition, what happens. Hold on, I'm trying to turn something up that luckily I don't think something was trying to download on my computer, an update. All right, so let's see why. Dorinda, that was you who asked, right?
Yeah, I was just like, just with like problems like these, for if you want to find the domain of like FGX, do you have to like kind of consider the like denominator of both like GX slash like the input and then the final like simplified version of the equation?
Yes, so you have to consider the inner function domain. You're absolutely right. The inner function domain as well as the end result. And I want to show you why. Like say I had asked you to do, so using these two functions, say I had asked you to find f of g of -1. The first thing you would do would be g of -1, right? So you'd plug -1 into the g function, and so you would be doing f of and putting -1 into the g function. It would be 2 over -1 plus 1. And what would you notice there? Like as soon as I try to put -1 into the g function, I'm running into problems, right? Because in a composition, because every x has to first go through that inner function, that domain is super important, as is the end result. But the domain of the outer function, like the f function, doesn't matter unless it's the same as the end result function, which it happened to be in this case. But normally the domain of the outer function just doesn't come into play because the outer function is being changed by that inner function. So just remembering, look at the end result domain and look at the inner function domain, because you have to consider both of those. And that's a harder, more sophisticated concept. I put it on the written assignment. And I probably also, you could expect it as part of a bonus. Again, it's a harder concept, I think, to sometimes get down, but important. What about like, so everyone look at number 5. What about if I had said, so I told you to find the difference quotient. What if I said find f of x plus 1 and simplify? So everyone try that. If I had said find f of x plus 1 and simplify. We did something similar in class on Thursday. Okay, let's see what, and then I want to give you an exponent one to think about. Okay, so remember what this means. This means wherever there's an x, I'm putting x plus 1. So we should get negative x plus 1, and we're going to square it, plus 2x plus 1 minus 1. Did people start off okay there? Okay, so the thing to keep in mind with this next step for simplifying is, notice you have this negative out in front of the x plus 1 squared. Make sure after you square x plus 1 that you distribute that negative. So I tend to, just to be safe, kind of put brackets or parentheses around when I'm squaring it. So it's x squared plus 2x plus 1, and then I'm going to have plus 2x plus 1, sorry, plus 2. Don't forget to distribute minus 1. And so we would get negative x squared minus 2x minus 1 plus 2x plus 2 minus 1. And seeing what this simplifies to, what are we getting?
Negative x squared.
Negative x squared. And yeah, very nicely, those numbers canceled and the negative 2x and the plus 2x canceled. So that actually worked out quite nicely. Did other people get that?
Wait, there's two negative ones, so wouldn't that be negative x squared minus 2?
Yes, and that can't, and luckily, if I did it right, that cancels with this plus 2.
Oh, okay, I missed that. Okay.
I think so, yeah. Because don't forget that when you distribute the 2 to the x plus 1, you'll get 2x plus 2. But you're right, you have these two negative ones, and luckily that's just kind of coincidentally, it ended up canceling with that 2. Usually that doesn't happen. Usually it doesn't work out so neatly, but because of the way this function is and what I picked to put in for the input, it just happened that things canceled. Okay, let's try. So there was on this sheet, where were they? Let's see if I can find. I gave you some practice with exponent stuff. I'm going to give you another one to see. So what if I gave you something similar, but if I said simplify, and you can have no negative exponents. So the cube root of y times 27xy to the 2/3 over x to the negative 1/3 y. So this is getting a little bit more complicated, but see what you can do. Let's take a couple minutes to, and my big advice is change all roots to exponents. Don't try to combine roots and exponents. Change everything to an exponent.
Is that more complex than what we should expect on the test tomorrow, or is that kind of
So I would say that on the so it would be a similar problem on the test, except maybe it would only, instead of this, in this problem, I put 2 variables and a number, and you're probably only going to have something with fractional exponents, probably 1 variable and a number. So for example, instead of having both the y and the x and these fractional exponents, it'd probably just be one of the variables, but similar types of concepts, being able to combine fractional exponents with both variables and numbers. So similar, but slightly easier on the test. Like I would say a kind of a easier one that is more equivalent to what you would see on the test is probably B, the one I already gave you. All right, who can start us off? What might be some like a starting point here.
You can make it y to the 1/3 instead of the cube root.
Yeah, I would definitely do that. So any roots, just make everything consistent because you're not going to be able to combine things until we make it into an exponent. So y to the 1/3. And then what do we think about? So whenever you have multiplication in a parentheses and all of it is raised to an exponent, what do you do about that?
You raise each like component to the exponent.
Yeah, because, right. And so when it's multiplication inside, or frankly, all division too, each piece means each piece is raised to that exponent. So that might be what I do next, because this means 27 to the 2/3 times x to the 2/3 times y to the 2/3. And then in the denominator, I have x to the negative 1/3 times y. Okay, so a lot of exponents. Well, looking at just the numerator, there is something I can combine. What can I do with the numerator?
You can add y to the 1/3 and y to the 2/3 to just get y.
Yeah, because, right, with the same base, so y and y, you can add the exponent. So y to the 1/3 times y to the 2/3 would just be y to the 3/3, which is just y, right? So I'll have y on top. What does 27 to the 2/3 mean? So let's go to the side here and do 27 to the 2/3. What exactly does that mean? What does the denominator of a fraction mean? Fractional exponent.
The root.
Yeah, so you're going to do the cube root of 27. So I always try to do the root first because it will make numbers smaller. And then you're going to square it. So what's the cube root of 27?
3.
3, and 3 squared is 9. Okay, so I've dealt with so I'm just gonna cross that. I dealt with that is not a good one to use. I've dealt with the y's, and I've dealt with 27 to the 2/3. So now I've got this x to the 2/3 still up top. And then I have x to the negative 1/3 in the denominator and a y in the denominator. So what next? What about division with the same base? What do you do with exponents when you're dividing with the same base?
Just
Or-
subtract to the top and the bottom, and then you'll just get 1.
Yeah, so I can, right. So I would do 2/3 minus negative 1/3, which would be x to the 3/3, which would just be x to the 1 on top. So it's looking like this. Another way to think about it, say you don't want to deal with negative exponents and don't want to deal with division, you could just have brought up the x to the negative 1/3 and make it x to the 1/3 in the numerator. And then you just add the exponents. All right, so in this case, I've got 9yx over y. Last thing I can do is what? Cancel out the y's, right? So it just ends up being 9x.
I have a question.
Yes,
Are we gonna have our calculators?
you are going to have your calculator. Yes,
Okay, so we can use our calculator to find like 27 raised to the 2/3.
you can. Yes.
Okay.
I bet you could do that without your calculator though, too. But yes, you will have that. Yeah, you will have that. And it won't be that big of numbers too. So, but you'll have your calculator the whole time. Yes.
And then also, is graphing the piecewise functions going to be on it? Because it wasn't on either the practice test, but it was on the written assignment.
Graphing the piecewise, no, it will not be on. But you should be able to do something like two, where if I give you an input, you just tell me the output.
Okay, got it.
Yeah, some things
How
I
long-
like to do on a written assignment versus a test. Say that again. Sorry, I interrupted.
How long is the test going to take? Like, how long is it designed to take?
Oh, that is always a good question. I try not to make, I don't think, I don't know. So good question. I don't know. It's not designed to say, if I were to guess, I would say a good chunk of you will be done in 40 minutes.
Okay, thank you.
But I want people to feel like they can take as much time as they need, particularly on this first test. Yeah, so I would say, and I think the biggest thing that that will determine the time is probably, although it's not that bad on here. Yeah, I'm gonna say 40 minutes. I was gonna say is people's ability to factor, but there's no, I'm looking at it right now, there's no weird factoring. In fact, I would say, so this review packet, by the way, on average is way harder than the test. Not way harder, but harder problems, I would say. Like the domain ones are harder on here than they are on the test. So yeah, I would say 40 minutes. But some things you just, like I just talked about on Thursday, you just have to know some of the basics, like how to factor, how to find zeros, basic domains, working with exponents. The difference quotient is a must. You're going to see starting after the test next week how often we're going to be doing the difference quotient. That is like the key to what we're doing next. So we got to get that baby down. Yeah, so I don't anticipate time being an issue for you guys. For my advanced pre-calc, that's another story, but not for here. What else you got for me? And if you don't have anything else, that's fine too. We feeling okay about domain stuff?
For number 13, it was like, it was a composition of functions, but like in a word problem.
Yes.
How do we determine which one is being inserted into the other one?
Yeah, that's a great question. So how you know is I look at the last sentence, because the last sentence said express the carbon monoxide level. So that tells me that that's my outer function. That's my Y value. In other words, I want to do carbon monoxide in terms of something. So looking at, let me go down to it. So in 13, so express carbon monoxide. So that is going to be my outer function. And let's write what so people know what we're talking about. Let's write what the different things are. So the carbon monoxide function was this. So C of X was equal to 1 plus 0.4X. And then the other function I gave you was the population function in terms of time. So P of T was 750 plus 25t plus 0.1 t squared. So I've got this. So once the first step is to actually write that down, which is helpful to write it in function notation. So I've got my population function, and then I've got my carbon monoxide function. And it wants the carbon monoxide function in terms of time. So that tells me that if my outer function is the carbon monoxide, the inner function must be this P of T, because that has time as the innermost. Also, I don't have another function, so that's the only choice for the inner function. So it means into my cost function, wherever there's an X, I'm putting this whole thing, 750 plus 25t plus 0.1 t squared. So that's why it was 1 plus 0.4, and then just putting this whole piece in for X and simplifying. And you'd use your calculator to do the multiplying to simplify. Yeah, good question. So look to that last sentence and it'll say express the whatever. And that whatever is your outer function, which by default, the other one will be your inner. And that was just kind of that was more of an application of compositions functions.
And we're gonna have the formula, right?
For which one, hun?
Like for all the problems with like all the
Yeah,
work.
so anything that you need a formula for, like the compound interest. And I think compound interest, I'm giving you difference of cubes, sum of cubes, and difference of squares.
Okay.
And that's really the only formulas you would need. But in the future, we will do more, hopefully people will start bringing their calculators and we'll be doing more with using our calculator. So something like 14 in the future would be expected to be able to do on our calculator. Believe me, you don't want to do it by hand by doing like polynomial ridiculous division, which you can do, but we're not going to do that in this class. So you want to be able to use your calculator to do something like that.
Do you think you can go over the first problem with like the domains?
Sure. Yeah, let's go there. So, talk to me, Sam, about what's the only two things we've done that we have to think about when it comes to domain? We can't, oh, go ahead. Sorry.
Well, I was just for like B, when we then had to like take into consideration like the numerator, I was more like focused on the denominator, so it sort of like confused
Threw
me.
you off a little bit. Yeah. So sometimes that, so yeah, so even in A, we've got kind of two things going on. And the things you have to worry about in the domain for domain is denominator can't be 0 and under a square root has to either be 0 or positive. So when I look at, let's do A of X first. So one thing I know is X plus 3 cannot be 0. And I also know that the square root of X minus 2 can't be 0. So denominator can't be 0, but because I have a square root, under the square root also, I know it can't be 0, but it also has to be positive because I can't take the square root of a negative. When we're talking about domains, we're not talking about I, we're talking about real numbers. So I really have two things going on. I need X cannot be -3. And the square root tells me that X has to be greater than 2. Normally, if I just had a square root and it wasn't in the denominator, I'd set whatever's inside to greater than or equal to. But because it's in the denominator, I'm just setting it to greater than 0. So looking at these two pieces, so sometimes I kind of find it helpful sometimes to then put it on a number line. I know that X cannot be -3. But it also has to be greater than 2. So when I think about the domain meeting both those conditions there, what must be the case for the domain? I mean, negative
2 to infinity.
Yeah, -3 is not greater than 2. So -3 doesn't even come into play. So it only, right, so it'd be 2 to infinity. So yeah, B is a little complicated because if I had just had 2 minus X on the top and had X plus 3 and X minus 3, you would tell me X cannot be -1, X cannot be 3, because both those numbers would make the denominator 0. But whenever you see a square root, I want you to think inside the square root has to be greater than or equal to 0. So with square roots, you're setting up an inequality. What do we know about absolute value? What comes out of an absolute value?
A positive number.
Yeah, so a positive number or 0. So isn't it always going to be greater than or equal to 0 in this case?
Yes.
Yeah, so no restriction comes out of this. Yeah, so this is always the case. So then my domain, the only thing I have to worry about for my domain is it can't be -1. And don't forget to put between -1 and 3, right? So there should be a break at -1 and it can't be 3 either. So that's it. So that one definitely was a little bit weirder because it had that, absolute value in there. What can you guys say about C of X?
I have a quick question about A of X.
Yeah,
Because we said that X cannot equal to -3, why did we not do negative infinity to -3?
oh, because the square root limit us to what we could put in, because it has to, all those X values have to go into that square root. Anything below 2 isn't part of the domain anyway, right? So if you tried to even put in 0, what would happen if you put in 0 for X?
It would be negative.
Right, exactly.
Got it.
So
Okay.
that was the issue, because I needed both it to, we're talking about domain, it can't equal -3 and it has to be greater than 2. Well, -3 isn't even in the greater than 2 part, so I don't even include it.
Okay, got it. Thank you.
So for C of X, if I look at both denominators and set them, say they can't equal 0, well, is it ever the case that X squared equals -1 or X squared equals -5? In other words, is it ever going to be the case where our denominator here is 0?
No.
No. So in fact, I can put anything in the denominator. So there's no restrictions on the denominator is giving me no restrictions. Those will never be 0, because for X squared, you're always going to get 0 or positive. So that will never be 0 when I add 1 to it. Same with X squared plus 5. So I have no restriction when it comes to my denominator, but I do have this square root issue. So inside the square root has to be greater than or equal to 0, which means X has to be greater than or equal to 3. So again, just reiterating that when you have a square root, you set whatever's inside greater than or equal to 0. And that's my domain. It's going to be 3 to infinity. So it was that square root that was limiting me, or limiting the domain, I should say.
So do you only like think about the numerator in these problems when there's a square root in the numerator?
Exactly. Yes. The only time and the numerator would ever play a factor is if there were a square root with a variable under it. Right.
Okay, that makes sense.
Otherwise, it's not going to impact it at all. The domain, that is. Okay, D of X. So we've got a bunch of things here. So each square root, remember, see a square root, you set up an inequality. So X has to be greater than or equal to 0. X greater than or equal to, well, actually, I'll step back a minute. X plus 1 greater than or equal to 0. X minus 1 greater than or equal to 0. X plus 3 greater than or equal to 0. And X minus 4. So you've got all these inequalities. So X greater than or equal to -1. So you've got the 0, the -1, 1, -3, and 4. So remember, it has to, because this is all one function, any X values I put in have to work in all of these. So thinking about it being able to work in all of these square roots. In other words, when I input it, I wouldn't get a negative in any of them. What would you have to go with?
X is greater than or equal to 4.
Yeah, you'd have to go with that one, the one that's the most limiting, because otherwise, say I went with X greater than or equal to 1. Well, that would be fine for everything except when I get to the X minus 4, then we'd be in trouble. So you have to go with the one that works for all of them. And that would be this most restrictive, which would be the greater than or equal to 4. Yeah, so your domain would be 4 to infinity. And again, these 4 are actually harder than I'll give, but they encompass all the types of things to be aware of. You want to be aware of, if you've got a square root, you got to set up the inequality greater than or equal to 0. And if you have something in a denominator, if that denominator ever equals 0, then that cannot be part of the domain. That was a good one to go over in terms of like hitting on those different concepts. So we probably have time for one more question if people want to do one more type of problem. Happy to do it or answer a question. Or if you want me to make something up. How do people feel? Are people okay with, so I said that I would give you the interest equation. People know what everything in it means? In the compound interest equation?
Can we go over it?
Sure. Like say, maybe I'll give a random one here. So what if I said, all right, we're going to use your name, Dorinda. Dorinda deposits 2,000 into an account at, let's see, 2.35% annual interest. How much will she have after 5 years if interest is compounded daily? Okay, so you see that and you realize, okay, I've got to use this formula. And the formula is this. And this is all that you'll have in terms of a formula. You just have to then know what the different pieces are and what you're solving for. So which variable are you solving for in this case? Anybody? What are we solving for here?
A.
Yeah, how much she'll have after a certain period of time, the amount, yep. So A, P stands for the principal. Sometimes people think of it the present value, how much money you have in the present, which is 2,000. 1 plus, talk to me about R. What is R?
Rate.
Yeah, it's the annual rate. And you want to write, the key is to remembering to write it as a decimal. Hopefully, if you don't, you'd be like, holy cow, she got a lot of money. Her money really kind of grew quite quickly. Yeah, if you're noting significant growth in your money and it's only 2.35% interest, then you probably wrote R wrong. So make sure you write it as a decimal, which would be 0.0235, which is 2.35%. What am I putting in for N? What does N stand for?
365.
Yeah, it's the number of times compounded per year. And in this case, daily, we're going to go with 365. That's exactly right. And 365 it ends up there as well. And T in this case, I said 5 years. T, by the way, in interest rate problems is always years. Like last year when you did maybe some exponential growth problems, T could be whatever in the, as long as you were consistent in the context of the problem, but an interest rate, it has to be in years. Okay, so if you have a calculator, remember, so that's half the battle. I will tell you, I'm gonna guess usually on tests like this, about a third put it in their calculator wrong and give me the incorrect answer. So let's hope that's not the case. Usually you can tell because it'll seem off your answer, but I'm going to put in my calculator now, just so if you guys don't have your calculator, you can check later that you get this. So let's see. And maybe someone else could do it, so you can double check me here. Okay, my first pass was getting that. I'm gonna do it one more time though, because I felt like I entered something in wrong. Nope, I'm still getting the same thing. Anyone else get that? Anyone else try it? Anyone else get something different? All right, we're gonna go with that being it. Okay. So does that make sense, that how to use that equation? Take that as a yes. All right. Any last minute things, or how are we feeling overall about this stuff? Again, if we thinking about the stuff we did in class on Thursday. Feeling okay? All right, I think you guys are gonna be good. All right. So I'll see you first thing tomorrow. And it'll be good. And if it's not, we'll just learn from our mistakes and move forward. All right, everybody, have a great night.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Thank you.
you.